Welcome. My name is Robbert Dijkgraaf. I'm the director of the Institute, and a warm welcome to the first, I hope, of a series of family talks. And so delightful to see so many children here, and perhaps some parents, which are just here, I guess, to supervise. That's the but I would like to ask the children if any of you want to sit here in the front, just on the floor, like these beautiful four girls are doing there. You're happy to join us. So, but you can also sit with your parents, whatever you want. If you want to sit up here, please feel free. So this will be a lecture about the smallest particles, and if you talk about small particles, you also start to talk about large numbers. So one thing I'm very happy is that we have enormous age range here in the audience, and I want to call attention to two audience members. First one is Luca Villani, who's over there, who's 5 weeks. And then we have Professor Freeman Dyson here, who will soon turn 90 years. And actually, if you calculate, that's roughly 5,000 weeks. So we have a factor of 1,000 already here just in the audience in terms of the age. So what I want to do today is actually try to, in a very brief time, bring all of you through a series of discoveries, which is basically going from our size that we all are to the much smaller elements. And the first question I want to ask you, suppose that the world would disappear, everything, but you are able to send one message to another, perhaps aliens on another planet, summarizing everything we know. And suppose you have to do it with a message, a tweet. So in 140 characters, you have to summarize all of science. So there are many solutions to this, and but actually, what I would pick is the following. So this would be my very last tweet. All matter on Earth and the cosmos consists of particles 1 billion times smaller than everyday objects. And why would I pick that? Because if you take an object like this, and you know it's made out of, say, particles, this is a piece of Lego, so I can try to make it apart. Not only do I learn that it consists of small bits, but once I have the small bits, I can rearrange them. I, in some sense, have control of what I do. Suppose you get a toy, and somebody, a car, a little toy car, and one is made of metal and the other is made of Lego. So then, suppose you go back in a year, and you ask, what happened to your toy? Well, the left one will still be the car. But I'm sure the right one isn't anymore a car, but it could be an airplane. So the lesson you learn today is that if you know what are the building blocks, you can start to build. You can make things, you can design. And that's actually basically what we have been doing for a long time. And in fact, that things are made out of small particles is a very old idea. Actually, already the Greeks used the word atom. They thought it was an idea they had, a very good idea. And they even had an idea how these atoms look like. They knew there were these 5 beautiful mathematical figures. That was a part of mathematics. So they thought, well, everything is made out of these 5 forms. And they had even a theory behind that. Because if you have these little cubes, they are literally like Lego blocks. You could build something solid. So anything solid, like a piece of rock, would be made of these little cubes. These kind of little pyramids, they have sharp, pointy edges. So if you would touch them, they would hurt. So fire would be made out of that. This figure here, icosahedron, it's beautiful round, so it could roll. So this would be typically water. And then there was another theory of air, but there was one left over. And in fact, what I thought that this beautiful figure, which is actually what makes up the rest of the world, outside the Earth. So the planets, the stars, the cosmos was made of this beautiful figure, the dodecahedron. And actually in art, you see many of these figures. They're very beautiful. It always stands for the world outside the Earth, about the cosmos. But actually, that is almost only theory. If you go back how we actually discovered this, we have to go almost 2,000 years later, which was the birth of modern science and the first microscopes. And in that time, so we're talking about the 17th century, people were looking through the microscopes of all kinds of things. And in fact, there was a scientific institution, the Royal Society, where people did this, tried to investigate things, and they had a nice slogan, a motto. It was in Latin in these days, nullius in verba, take nobody's word for it. Just look with your own eyes. Look in the microscope and look what you see. And there were beautiful books, and these books were bestsellers. For instance, this is the book by Robert Hooke, Micrographia, and there were beautiful pictures in. For instance, this was a picture of a human flea. It looks like a giant monster. But just to know that this little animal is living on your head, that was just made people like totally crazy. So you could imagine, it was like, oh no, they're like dinosaurs or something, but they're on our head, they're everywhere. And so they could see a lot of things, but the amazing thing is that the real breakthrough came from somebody living in the Netherlands, actually, Antoni van Leeuwenhoek. And he had some very crazy idea. He said, let's make a bigger microscope. And you might think a bigger microscope is which can see more, will be a bigger instrument. But he did exactly the opposite. Oops, this is not the original one. It's a replica. But this is the thing he made. It's really tiny. And it has a very small lens. He made a microscopically small glass ball, looked through the glass ball, and he saw things. This is magnifying almost 500 times. He saw things that nobody else saw. In fact, what he saw was little animals. He saw little animals in water. He saw little animals in his own blood. He saw animals everywhere. And in fact, if you look, for instance, at a leaf, you see the same kind of little structures. And people looked at this and said, well, this reminds me of the monasteries where people would live in little chambers, little rooms, which were called cells. So this was the moment, in some sense, where the word cell entered. And so the crazy idea is here that we ourselves, human beings, and actually any kind of big animal, is not the right way to think of it. So I took this Russian doll here. So in some sense what we discovered, so I have to do this carefully, that you could kind of open up a human being. And there's another level inside, which is much more interesting, which is the notion of a cell. The cell is much more the unit of nature. It's very small to see. The biggest cell is as big as a grain of salt. You can just see it with your bare eyes. But they're everywhere. If you look at all the biomass, so everything that lives on Earth, roughly half of it is made of these microorganisms, little bacteria and cellular animals. In fact, in yourself, if you count the total number of cells, you roughly have 100,000 billion cells. 90% of it are bacteria. They're not you. And for 2 or 3 billion years, the world existed entirely in terms of these microorganisms. So they think they're extremely successful. And you're just amazing that if you think about how many cells are in you, it's just, I say it's 100,000 billions. And at some point I will use big words. So one thing I want you to remember, at least the one thing you should take out of this lecture, is how big a billion is. So for that, I actually brought a bucket of sand. So this is very fine sand. And this is roughly a billion. So just think of it, that 100,000 of these buckets full of cells are in you. That has to kind of sink in. That's really big numbers. So we know that cells are really kind of the structure in which we have to think. And so just to visualize how you should go in, here's a little piece of grass. If we zoom in, so now we are at the size of 1/10 of a meter, 100th of a meter, 1,000th of a meter. You slowly start to see little structures here, 10,000, 100,000, and here we are at the level of 1/1,000,000th of a meter. That's the level where we see the little cells. And in some sense, this is a much better way to think about nature. It's the cells that make things up, and sometimes they form big colonies, and everybody here in the room is a big colony of these cells. So this was in some sense kind of a good unit to think about how to organize nature. But then we can zoom in even further. So here are these cells. Here are, for instance, cells from, these are bacteria, which are really very small cells, much smaller than the ones that are in a human being. But can we go even further? So what happens if we zoom into the interior of a cell? You see there's something very funny coming here. And here we get at the level of 1/1000th of a meter. And that actually is what we are seeing, what's inside a cell. So it doesn't stop, and what we see inside the cell are molecules. And molecules are everything where matter is made of. So we notice that cells are not the right way to think about it. The right way to think about it is in terms of molecules. And there are various kinds of molecules. There are very small molecules, like in a glass of water. There are very long molecules that are in your DNA. There are many of them. But if I ask you now, who was the first person who really proved that there are molecules? You will be surprised as this one. Everybody knows who he is? Yes. Yes, Dr. Albert Einstein. Of course, here is he at the Institute at a much later age. But he, actually, when he was a young man, and he looked more like this, he had many, many famous discoveries. But one thing that he discovered, how to prove, essentially, that there are molecules. Because I can tell you there are molecules, but how do you know? You don't have a microscope that's small enough to see them. But you can do the following thing. So what this is a movie where you actually look at a glass of milk. So if you have a glass of milk, you look under the microscope, this is what you see. And you see little bubbles here, and these bubbles are little bubbles of fat inside the milk. So they're not the molecules. But you see they are kind of moving around. And so the question is, why are they moving? Anybody idea why they are moving? What makes them move? Yes?
They're lighter than the milk.
Yes, but why are they not standing still? Yes? Yeah?
Because they're not a solid.
They're not a solid, they're a fluid, so they can move. But why? Who makes them move? Yes?
The water molecules?
Yes, exactly. That's the thing. It's the water molecules that are kind of bumping into it. And so what Einstein showed, that if you calculate this very carefully, you can basically see how big these molecules are. This is a physical effect, and you can calculate. And so basically one thing I want you to go with me is kind of try to visualize, if you have a glass of water, how many of these molecules are there? Now, it's difficult to visualize, so I have something else. I have here this box of chocolate sprinkles. So chocolate sprinkles, very Dutch phenomena. We eat this on our sandwiches. Here you sprinkle a few on a birthday cake, but we eat this in large quantities, actually. You know, well, one box a week at least. So an important question is, how many of these chocolate sprinkles are there in the box? Has anybody an idea? Well, you already have. Who wants to make a guess? Yes? 100,000. A million? Million? Yes? 500.
Maybe it's about
1,000. Okay, so let's just see. And so, for instance, it's easy to think about one chocolate sprinkle. Here we have 10. Here we have 100. Here we have 1,000. So you still think there are 1,000 in here? No, more, right? 10,000? What do you think? More? 100,000? Yeah, it's getting in the neighborhood, right? Here, that's you see that's a million. So I think actually we see it's roughly between 100,000 and a million. So I think actually there were some very good answers, you know. You guys who said 100,000, a million are very close. But a million is, of course, a good number, but now you can go further than a million. So a million is 1,000 times 1,000. Suppose we take 1,000 times bigger. So then this would be 1 billion chocolate sprinkles. So this is something that we eat per year, I think. That's roughly our... And again, if you, it's difficult to bring 1 billion chocolate sprinkles, but I can bring 1 billion grain of salts, and they're in here. And actually, this helps you think. For instance, if you think about how many people live on the world, it's roughly 7 billion. So you should think of 7 of these buckets full of sand. That's pretty amazing. Now, if you look at how many people in the United States, it's 1/3 of such a bucket. So you can try to visualize a billion. But of course, we can go much further. For instance, we can go to a trillion. A trillion is a million times a million. So if I would actually bring chocolate sprinkles, it would actually be a very powerful image. You would go here to the institute, you have this big mountain of chocolate sprinkles. And so let's go further. Suppose we take a million times a million times a million. So now we're learning some new words. Quintillion. So I couldn't even bring it in Princeton, but we could go to New York City. And actually make, so that actually you would see, you would drive into the city, you would really see a quintillion. But you see, we're still not there. What I need you to learn is a million times a million times a million times a million. So septillion, a 1 with 24 zeros. And this is the highest mountain on Earth. Does anybody know what the name of that is? Yes? Mount Everest, Mount Everest. So suppose we have a septillion chocolate sprinkles, that would stand out. In fact, if you would be orbiting in space, this would, you would see. So if you want to understand how to think about molecules, you should really think that, if you really want to see them as the way you see chocolate sprinkles, you will have to magnify that glass water to this level. So suppose you really go there, it would be something you could see from the moon. In fact, even further down. So it's wonderful that we know there are molecules, but they're really, really, really tiny. On the other hand, they can also sometimes be very tall. For instance, in your cells, we saw already the picture of a DNA molecule. And a DNA molecule, if you take one of these molecules, a long string, it actually is roughly 6, 7 feet long. So in every cell, there's a piece of string 7 feet tall. Just in a single molecule. It's one enormous molecule. And if you see the text that is kind of printed on that, if you would write it in terms of real books, it would be as much information as 4,000 volumes in one molecule. And if you say, how does nature do that? Because it's really, really tiny, these cells. We can kind of put there's a lot of space in to hide kind of these molecules. And of course, there are all kinds of molecules. Now, these are more complicated ones. This is a really big molecule. And sometimes we have very small ones. In fact, you have molecules which look very much like the things the old Greeks were thinking about. This is a molecule that looks like a soccer ball, a buckyball. In fact, if you just take a little candle, and the root in the candle, just the smoke, it has little molecules like this. So they're all around us. You can't see them, not with your naked eyes, not with an ordinary microscope. But we can understand the world around it. And if you ask, well, okay, why do I need to know this? No. Well, first of all, I think I should show this first. This is an animation. It's made by a computer of if you would kind of zoom into this cell and you would see it at the level of molecules. You see the molecules are like the little workers in our cells. They're doing all the complicated things. So you see these big strands. These are pieces of DNA. You have the proteins. It's all going on there. So it's like really a big factory. So this human being is made of all of these cells. And each of these cells are big factories where the workers are the molecules. And actually, we understand most of the things that are going on in terms of these molecules. In fact, if you take even a very simple question, for instance, the question, why is grass green? Why? What do you think? Sorry? Chlorine? Close. Yes, chlorophyll, exactly. So if you look at grass and you want to know why it's green, it has to do with the property of a special molecule. There's a molecule there called chlorophyll that actually is very good in absorbing the light, but just happens not to absorb the green light. So the green light it can't use, and it will reflect back, and there where you look at the grass, it's green. But it's more powerful. Look at any object around you. Now you can ask, why is the glass transparent? Why is this leaf this particular color? Now, why is that paint yellow? Any question about any material, we can only answer because we know the properties of the molecules. So actually, if you would go back in time 100 years, the children here would be able to ask questions, all kinds of questions about materials, of anything you see around you, that scientists would not know how to answer. Because at that time, they didn't know about molecules, they didn't know about their properties. And it's only now that we understand the molecules that we actually can understand more and more and more. And in fact, some people say, well, what do we know about it? For instance, the chlorophyll is a very good molecule to capture the light of the sun. And that's why nature is green. That's why trees are green and grass is green. So some people say if we ever go to another planet, the life we find there is probably also green. So that's why we have little green men. I like that theory. So I said we would kind of zoom in, but of course the molecules are not the end of the story. You already see that if you look at the pictures of the molecules, there are these little balls, and these balls are atoms. So the molecules themselves, although there are many, many of them, they're not the final story. They're made out of building blocks. So even the molecules, if you understand all of them, you can open it again. And there's a little other Russian doll, which is the atom. So actually, if you go into the realm of the atom, it really becomes complicated. Atoms have fascinating properties. In fact, these days, we can make pictures of atoms. This is a picture of a piece of gold. And you really can see the individual atoms here. It's not a picture made by light, it's a picture made by using electrons, but actually you can visualize them. In fact, one company even wrote its own name in terms of atoms. IBM, these are individual atoms. You can put them and place them and make the smallest advertising sign ever made. I think it should have written IAS. It's easy to fake, by the way. So understanding these atoms is really kind of a mystery. So the atoms are really, really small, we said. They're even smaller than the molecules. But they have another funny property. Because if you would like to visualize an atom, then you find something absolutely mysterious. And this is something that really scientists had a difficult time understanding. So suppose that this dining hall was an atom, and you would move into the atom. What would you see? What would you see? Where is the matter? Yes? In a nucleus, exactly. So what the people found out, that if you would go into an atom and you would look, you would see actually nothing. It would be empty. So if this whole dining hall was an atom, all of the matter would be concentrated in this little peppercorn. Isn't that amazing? So suppose you would have a very strong press, you could take an atom and push it all the way down to this little peppercorn. So essentially, anything is basically empty space with a little bit of it. So suppose you take a real mountain and you press it into each other so that basically all the empty space disappears. Then the mountain would be roughly this big. But it would weigh as much as a mountain. So who of you would be able to carry that weight? You would? Isn't that amazing? It's basically all the matter is concentrated very much in the core of that. And so how should we think about these atoms? And this was something that actually was only the first one who really started to understand this was Niels Bohr, and he discovered the way in which the atom works 100 years ago. So we now, in the history of physics, we now roughly 100 years ago. And he found some amazing things. He found that the atom has this little nucleus inside it, which has all the matter. And there were like little particles, electrons, were flying around. And they were flying around in a very strange way. So you might think it looks like a planetary system. They were going on certain orbits. But that was not the property that he found. He was actually finding, and many other physicists were finding, that the properties of these particles were very strange. They were ruled by chance. And so in some sense, once you try to understand atoms, you have to understand them essentially using some kind of a magic. So I want to illustrate this about what the funny things that these little particles can do. They can do things that are basically not possible. So I might be a little bit rusty, but then let me try to explain what they can do. So for instance, here I have a little particle. I put it in the cup. Oh, of course it's here, right? So if I have one empty, and I put this one, it's here. And if I look again, they're here again. That's easy. But in quantum mechanics, you can have something else. You can put it down again. And so where is the little red ball? Here? You sure? I think it's here. So you can put it back here. So it's here, right? So I don't know how it works, but that actually is, now here it's of course a magic trick. But if you are a small particle, you're like that. Sometimes you're at one place, sometimes in another place, and actually it's basically random what happens. It's a chance, you just don't know. Things can be at two places at the same time. And some say they were one place and the other place. And this is extremely difficult to understand. And in fact, there were many people who couldn't believe that. They couldn't believe that nature works that simple, that way, that it works by basically like something which is totally like flipping a coin or rolling a dice. And in fact, Einstein and Bohr, perhaps the two most famous scientists, physicists at that time, had very intense debate about it. Bohr actually liked this thing. He said, well, no, that's just how the nature works. And Einstein famously said, well, God doesn't throw dice. No, that's not how they work. And in fact, it's interesting that here where we are at the Institute for Advanced Study, they met many, many times. So here's a picture of them where they were older men meeting here in Princeton. And they had this very strong debate. Now, how does physics work? Can these things that you just saw with your own eyes, could it be that nature works like that? It's very funny properties. So again, if you kind of zoom in into an atom, you see it's empty space, and then there is this little nucleus, the little peppercorn in the middle of it. So what you find is that an atom consists of this little nucleus, and there are electrons flying around the electron. So we thought we were done with this Russian doll, but actually it's not true. If we make up the atom, there's lots and lots of empty space, and then inside is another Russian doll, the nucleus. So at this point you might say, well, now we better stop, right? We have done 5 steps, so this is the end of the story. But actually it's not, because you can again try to take a bigger microscope and zoom into the nucleus. And you see actually there are again little particles there in the nucleus. And does anybody have any idea what the name of these particles are? I think there are some guys here there. Yes, you. Protons and neutrons, exactly. So the nucleus itself can be taken apart. And there are elementary particles, there are particles inside the nucleus, neutrons and protons. And if you take them apart, something very special happens. I won't write any equations here, but you know all these equations, right? How would you pronounce that? Okay, and can you explain what that equation means? That sounds very good. So I actually have somebody who can explain the two here.
In which energy is first equal to mass multiplied with the square of the velocity of light, shows that very small amount of mass may be converted into a very large amount of energy.
That's the original discoverer of the equation, right? Albert Einstein explained the equation. So what it tells you that if you actually, there's a lot of energy in these particles. And just to give an indication, if you would take, again, a little peppercorn here, and you would make this peppercorn in energy, how much energy do you think you would get? What you can do with it? Yes? Yes? Like what kind of explosive? Exactly. So a nuclear explosion would roughly be the amount of energy in this peppercorn. And if you take like an apple or something, you could actually have the enough energy to run for a full day all of New Jersey. So that's tremendous amount of energies in these little particles. And in fact, one very big energy machine, energy source that's there, of course, is the sun, and that's actually how the sun works. So we have these particles over there. So is this the end of the story? So let's go further down. And you see there's something in this. Somebody have an idea what inside the nucleus? Yes, you. Quarks, terrific. So there's no need to give these lectures here, you know. Just it's the smartest audience I've ever seen, you know. Indeed, there are little particles inside the nucleus. So let's open it up. Well, first of all, I should have opened this. You know, we have seen protons and neutrons. I forgot about that. And then you were very smart to say that can be open again. So here there is the quark. There are quarks inside. So how do you think we actually see these particles? How do we see quarks? If there's a big microscope, anybody idea how we see them? What is the kind of microscope you use for that? Yes. No, not a telescope. How do you think it's the biggest microscope on Earth? So I showed you one of the smallest ones, which is this. But where do you think you can find the biggest microscope on the planet? Yes. Not even an electron microscope. Electron microscopes are big machines and you can see atoms. But you can't see a nucleus and you definitely can't see a quark. So where do you think is the biggest microscope? Yes? Yes, you. Yes, at CERN. Very good. Actually, it's particles. This is. Oh, I've seen many of these images. So you have seen that before. That's a huge accelerator, particle accelerator, close to Geneva. This is Geneva Airport. And at some point, if you're a particle physicist, you have to see too many of these pictures. So when the plane lands, you expect to see this big circle, but it's not there, you know. It's 100 meters under the ground. And particles are going around at tremendous speed. So if you, going around is 27 kilometers. And particles are roughly going around 10,000 times in a second. So you say, bah, and they go, brr, 10,000 times. And then they smash up very strongly. And it's, of course, done by many, many countries. And here under the ground, you have these very big magnets that make particles go around. And in fact, what is interesting too is that that is not only one of the most exciting places, not only the biggest microscope we ever built, but you know also if you go inside, it's extremely cold. You know, inside the particle accelerator, it's colder than in outer space. It's the coldest spot perhaps in the universe. It's there under the ground. And the particles go around, and then sometimes it's really, really, really nasty. So they go around. You should think of it as a big highway where one particles go left, the others go right. And then there are moments where somebody kind of rearrange the traffic in a nasty way, so they kind of collide head on. And they do this in this kind of big detector. So here you see the particles, here they go inside here. And this is the detector, this is the part where they actually collide. And just to see, this is a human being here. So I thought of kind of bringing a scale model of this, so that actually if I bring a scale model of this detector, so here's the institute, it would look like this. And the amazing thing is it's all filled with electronics. So think of your computer or think of your cell phone, how that's full of little microchips. This whole thing is full of microchips. And the amazing thing is it's buried 100 meters under the ground and it will never come out again. So just think in a few thousand years, people do excavations and they will find this big thing down. Yes? Well, think about the Lego. You know, suppose I want to know what this is made of. What I do is I put force on it. to break it up. And when I break it up, I can see what are the building blocks. So the same way with particles. Actually, to know what's inside, you usually have to destroy it. So they take the particles, they have them bang head on, and then see all kind of pieces flying away. And amazingly, they find all kind of particles. Now, they only find quarks, they find other particles. And the amazing thing is these particles, they are only made on Earth. So it's like they have a little brand name. We actually can make new things inside the particle detector. We can take pure energy and make it into new kinds of matter. And perhaps you have heard, so this is the picture what you get from the computer, where two particles are kind of banged right on. This is as big as this big detector that we saw outside, so it's as big as the whole institute. And these lines that you see are all the little particles flying off. And if you carefully reconstruct what's happening there, you can discover new particles. And perhaps some of you have heard that last year there was a new particle discovered. Who knows the name of the new particle? Who knows the name of the new particle? In the back. You say? Higgs boson, exactly. So this is Mr. Higgs. And here was a picture of, we had a little celebration here at the Institute too last year. It was actually on the 4th of July, which is now called Higgs Dependence Day. So see, we had a little toy model, because it's just the Institute, we're very small, we can't afford a big detector. But so we had a little, and we had champagne to celebrate this. And this is really the amazing thing of understanding these small particles. Because if you shoot two particles head to head, and you see what happens, and this kind of happens. And how we call this? Call this a big mess. This is chaos, it's garbage. Can you actually understand this? And the amazing thing is that many people thought, well, we can never understand. We shoot particles, some things come in, some come out. But the amazing thing is that it turns out that this little black box could be opened. And there was actually a formula inside. People can actually compute, and they can calculate. So here I use kind of really nice way to write the formula. So if you ever go to a physics talk here at the Institute, you will see more formula like this. So this perhaps it's a little bit more involved than E equals mc squared. But the amazing thing is that in the same way you can also say, I can actually put this formula on a t-shirt. The way we understand everything you see around you is in terms of, it used to be 16, but now 17 different particles. Everything. So if you go for the little particles, we can make up the nuclei, the particles like protons, they make up the nuclei make up the atoms make up the molecules. With the molecules we make cells, and if the cells form big colonies, they can form a human being. And everything you see around you is constructed out of these 17 particles. In fact, most of them you won't use. You use only a handful of them. So that's, of course, absolutely terrific, that we understand everything, and that's. So you say, finally, you're done. This was the last Russian doll. There are 17, and we're finished. And in fact, if you see how we understand that, we know exactly what kind of things these little particles can do, and we can compute. So they can go around, they can shoot particles to each other, and all of these possibilities we can compute, and we can do it very carefully. In fact, we can compute some of these things. It's the most careful computation, precise computation that human beings can do. And we can measure certain things. It's like measuring the distance from the Earth to the moon until the length of a hair, the width of a hair. It's like in a million times precision. So that's absolutely astonishing. So we have this thing we call the standard model, which is these 17 particles and their various properties. And we are very happy that we understand the world, because actually using that knowledge, we can understand many of the properties of almost all of the properties of matter around us. So we think this is a good moment to close down the Institute and all go home and do something else. But why not? It's actually not the end of the story. Because we still start thinking about it. For instance, we start thinking about, well, why 17 particles? Why in this particular way? And every time we thought, well, now we have reached the last Russian doll. So the question, of course, can we open this one, and what will be inside? I don't know, but we want to think about it. And there are certain things that really are amazing. For instance, one thing that physicists do, they put the particles and they say, well, suppose I rearrange them in a different way. Can I not see some kind of pattern where they all fit in a very nice, kind of more nice symmetric way? Isn't there a way we can kind of unify all these particles together? Or we go and measure, we see what happens out there. Are there any phenomena, is there anything which cannot be explained by these particles? And there are funny things. For instance, you wouldn't know, but actually the universe itself is a big accelerator. Actually, out of space, sometimes particles come in, and they hit the Earth atmosphere, and they form these huge cascades, these kind of avalanches of particles. And if they come, they cover an area of many square miles. And so there's funny particles flying in. We don't know exactly what their properties are. And more amazing, if you look at the universe, we see actually there are many things we do not understand. For instance, this is a picture of a galaxy, like our own galaxy. It contains hundreds of billions of stars. But if you start to measure actually in the universe, it looks like these galaxies are surrounded by a huge cloud of matter. And that matter is not matter that we know about. We call it dark matter. And in fact, if you look in the universe, astronomers look in the universe now, and they find a lot of these dark matter. And in fact, roughly 6 times more than the ordinary matter that we can describe using our Russian dolls, the small particles. In fact, they can measure, in some sense, the weight of the universe, and they can see how much of the universe can we actually explain. And physicists and astrophysicists find that roughly 5% of the universe we can explain. So 95% of the universe is still left open. So what's that made of? So we think some of it is made of a new kind of matter, dark matter, and others made of a new kind of energy we call dark energy. But it's just beautiful words to say that we don't know what we're talking about. So 5%, is that good or bad? I think it's pretty good. And we've done it in a very fast way. In a few hundred years, we're done to 5%. But it's clearly not the end. So there's a lot of things to be discovered. And so in some sense, we are almost back to the Greeks, where we say, well, what's the way to understand this? And we can do this in terms of experiments. That might take a long time, but we also do it by thinking, by theory. And so perhaps you've heard that there are many kind of theories around, but one theory that a lot of people here at the Institute work on is called string theory. And the final thing I want to show you is now, suppose you would really be able to go down to the smallest particles that you can think of. How small would that be? So you've seen we have used 1, 2, 3, 4, 5, 6, 7 Russian dolls. So we kind of think we know where the answer is, but you will have to go 1 step, 2, 3, 4, 5. Oops. There you go. 6. You see, that's a long way to go. Oops, there you go. And then finally, we have this Russian doll. There's a little string in it. I'm not going to tell you about string theory, but it's a theory where we think that the world doesn't exist of little particles, little balls, but little rubber bands that can vibrate and can oscillate. And that theory, it's at this moment a theory, it would be wonderful if that describes nature. But you see actually how long a distance we have to go to actually start to measure all of this. So in some sense, we are almost like the Greeks, which were thinking, this is the scale we were thinking about atoms, and they're somewhere around here. And so we have to go many more steps to go all that way. So I want to kind of finish by kind of recapping the thing, and I'll actually show you a little piece of a movie called Cosmic Voyage that actually I like because it starts in the Netherlands, and it's recapping.
Antony van Leeuwenhoek perfected the early microscope and used it to study droplets from the waterways of Holland. As students today make their own discoveries, imagine the moment when van Leeuwenhoek peered through his more powerful instrument and discovered a living kingdom in a drop of water.
We are here at this level.
Paramecia is only 1 millimeter across, 3 powers of 10 smaller than a meter. The microscope allows us to continue our journey into the realm of the very small. As we move into the cell nucleus, each new ring now reveals a world 10 times smaller in diameter than the last. Deep within the nucleus,
Here are the molecules.
we come upon truly remarkable constructions. Long, spiraling molecules of DNA. DNA holds the chemical codes for the reproduction of most organisms on the planet, whether they're paramecia, people, or petunias.
Here you see the atoms coming. We're at the 4th level.
Voyaging on, we see that molecules are made of even smaller parts called atoms. The tiny world of the carbon atom is very strange indeed. Its 6 electrons seem to swarm everywhere at once.
See the empty space.
Voyage takes us through a void that appears as vast as the space between the stars. Ahead lies the atomic nucleus, so fantastically small that if the whole atom were the size of this theater, its nucleus would be like a speck of dust. Yet the nucleus contains almost all of the atom's mass, packed into particles called protons.
We are here, the protons.
And these, in turn, are made of still smaller, mysterious things called quarks. Exploring this, the inner frontier of the universe, physicists wonder if quarks might contain even tinier building blocks of matter.
So here the movie stops. And when I first showed this movie to my children, they said, how does the movie continue? And actually, this is exactly what physics is all about. So I don't know what's in the next Russian doll, but I hope some of the kids who are here, some of you will actually become perhaps physicists, and actually will discover this. And I just hope that when you discover it, you let me know. Okay, thank you very much. Are there any questions? Yes.
How small are the water molecules? 1 nanometer?
Yeah, exactly. So 1/100000th of a meter. It's a bit smaller perhaps, but a typical size of a molecule is a nanometer. Very good. Yes. You.
How long do you think it will take for people to discover the even smaller things?
Well, I think we hope that the big accelerator that we show, the LHC, it's now being upgraded, so it's made even stronger, almost 10, 15 times stronger. And then so in a year, it will start running again. And then we hope we'll find some new particles beyond the quark and the Higgs. So it could be that in 2-3 years you read about it, but we don't know. Sometimes you have to wait a longer period, and perhaps you have to build the next machine. That's the big question, I think. We don't know. Actually, if you think about it, I think when people discovered cells, they thought that was pretty good, you know? And that's it. And then you discover the molecule, think, oh, okay, now we're done. You discover the atom, oh, yes, fine, finally. And every time there was another layer. But we kind of know that if, in terms of if you go shorter, that at some point at this very, very end here, the last doll, which is really much smaller, it's like really going from the human being to a quark and then going in the same distance, that you can't really go smaller than that. That's kind of the smallest distance there is in nature. So at some point it has to stop. But how many dolls are between these two levels, we have no idea. Yes.
Wouldn't the smallest size be 1 Planck?
Exactly. It's called the Planck unit, and it's actually the size where, if you think about space, space itself could be like if you zoom in a computer picture, you know, you have the pixels of your picture, and if you zoom in, at a certain point you only see dots. It could be that space is like that. And then the pixel size would be the Planck scale. And so the Planck scale is exactly the size where this smallest Russian doll is. Yes. Well, actually what happens is that the molecules and the atoms, at some point they go into the air and everything, and it's a very strange idea. But, you know, in some sense these molecules are recycled. The atoms are recycled. So in fact, you know, you have in yourself atoms that have once been a dinosaur. Perhaps you have an atom that has been part of a dolphin or a mosquito or a tree. So we're all big recycle engines. Yes. If only we'd know. That would actually. So in some sense, you know, you have the history of many organisms. Basically, anything that lived, left at least a few atoms that are inside you. But that's a good question. You know, actually, it's good to know that this accelerator, they start thinking about it 30 years ago. They start building it 20 years ago. And roughly it started being operating 10 years ago. So you really, and then I think we use it for another 10, 20 years. So it takes altogether perhaps 50 years. And in fact, Peter Higgs and the others who invented this idea discovered this idea of a Higgs boson, that was almost 50 years ago. So first you need 20 years to think that's a good idea to build the accelerator. But the great thing is it's like you have one microscope that the whole world uses. So in that sense, it's very efficient. You have only one machine, and the whole world is using that huge microscope, which is very different from the old days where everybody had his own little microscope. Yes? So you might think that indeed you can go zoom in, that you say. It just never stops. And the reason why we think this is not true is that at some point, because if you zoom in, you know, you use basically the ability to kind of magnify space. So at some point we think that space itself will stop, can't be magnified anymore. So it's really looking at a picture. Now, if you get a picture on your camera, and you kind of zoom in, and you know it's like a 4 megapixel camera. You know, you can zoom in. At some point, you don't see anything anymore. So we think that actually nature is like that. It has a finite amount of pixels. Yes, in the back. What people do here, actually, they do two things. They think about the equations that describe what's happening in the big machines, and they are getting information about the particles, so their properties, etc. And then they check whether the properties they are confirming or not what they do with their equations. So you should think of it, it's not like one person working the big machine. It's more than 10,000 people are working in the machine. Some are building it, other are doing the detectors, other are doing the computations. And they're also not all in Geneva. They're across the world. So for instance, also the data that are measured there, they distribute it across the world. It's basically too much. So it's like all this information is coming out, and with these big buckets, they send the information to other laboratories. So everybody is sharing this. So people are in contact, but they're not actually. And some of our physicists go over there and work with the people who make the machine. Yes?
What is that small doll?
This was the string theory. This. This one? Well, so this would be the smallest size that's there in space. So we know this is the last doll, and perhaps there's a little string inside, but we don't know for sure. That's the big mystery. If you can open this one. Yeah. No more questions? Well, thank you. Yeah. Oh, sorry. Yes. One more. Yeah. Two. Ah. That's privileged information. Oh, you can come down and tell you how the trick works. And so the very last question. Let me stop. So here we know there's nothing in between. But how many dolls are here? We have no idea. We simply have no idea. Okay, thank you very much for coming.